m dot, which is the flow, the mass that I'm putting through there, m dot, the flow that is actually going through here, multiplied by the changes in H, the enthalpy. Now it's H2 minus H1. Actual or isentropic?
Actual.
If I want the actual, I could get the actual. If I want the isentropic, I could get the isentropic. So, meaning I just need to understand which is actual, which is isentropic. Work in actual is equal to m dot H2A minus H1. Ideal is equal to m dot H2S minus H1. So, what's the difference between both? Which one's higher, which one's lower?
Isentropic. Actual is higher.
The actual is higher. So, is that an efficient process if I want to compress gas? So think of it as you have a problem and you want to compress gas from a atmospheric pressure to 30 atmospheres. And you want to run a crank, right, with your hand. That's the work that you're doing to get it up from 1 atmospheres to 30 atmospheres. It takes you 10 turns to get the actual work versus 8 to get you to that work. Which one would you prefer? A, which is the ideal process, right? I'm trying to simplify it as much as I can so you understand it. So when we get into complex engines, you completely understand the difference between actual and isentropic and ideal. So essentially, yes, you end up, because of losses, think of that, that crank that you rotate as it wears off over time. And the gears on there are getting bad with a lot of tolerances. The tolerances are increasing, and you have to turn more. Well, it's more losses. And in this case, it's friction between the gears, right? So it's the same principle. It's, you have losses that happen inside that result in the actual versus isentropic or ideal process. But you know what you should get as an ideal process, but you never get. This is practically impossible, because we already said you can't get it. But you know the reference point. The idea is to relate it. So how do I find my efficiency for my compressor is equal to, I don't have to do the enthalpies. I could just say it's what? It's work in ideal over work in action. So what does it say? It says that if I have, and most likely your compressors are around somewhere between 70% to 80% roughly efficiency. That's the efficiency. It's primarily a component efficiency. It says if I get the component efficiency up, I could get more work or less work that I put in. Where's that work going to come from? Probably some device you're using, or your hand, or in our engine specifically comes from the turbine. Okay? Does that make sense to everybody? So enthalpy here, the efficiency in terms of enthalpy changes. Well, with the ideal, what's going to happen is m dot H2S minus H1 over m dot H2A minus H1. This cancels out with this. What formulation that looks like this? Bless you. Diffusing. Just did it. So it makes sense to everybody? All right. So so this is all thermodynamics. There's nothing to do with propulsion yet, but I want to make sure that these fundamentals are well ironed out before we move forward. Do we have a question?
Yeah, I just wanted to be clear. The W in those equations, was that supposed to be a rate of work, or was that just W by itself?
You tell me that.
So
it's a good point. Good point. Well, is it rate or non-rate? Rate. Why rate?
Because there's m dot.
Because of the m dot. So that's very correct. I didn't have the dot there, but the understanding is that we have a rate-based system. you get used to at some point that you have to take the rate into consideration as part of the propulsion system. So, but that's a good point. If you're working with static systems, you have to account for work as rate. So before I get into gas mixtures, I wanted to lump in most of the equations that we have and related to a propulsion system, so that first is excite you a little bit, because so far, usually this portion of the class, mostly it's review. I mean, that's what it is. I'm reviewing the fundamentals, and unfortunately, this is a sour part of the course, okay? So it's understandable, but the fun stuff is gonna come, but you can't get into the fun stuff until you know the fundamentals very well, because then you're gonna be lost. So you're gonna appreciate it later on. So let me just do a simplified problem in terms of a propulsion system. We're gonna assume, we're gonna make simplified assumptions because we still need gas mixtures, we need reacting mixtures, and we're gonna go add compressible flow, which is high-speed aero, to review before we actually apply it to the propulsion system. However, I'm just gonna do a simplified problem based on just gas turbine engines. So let's do a design problem to get us excited. Okay. So construct a model for the Brayton cycle. Or gas turbine engine. We're gonna have to make a few assumptions just because we need to go over some of the gas mixtures, reacting mixtures, and compressible flows like I just mentioned. So, assumptions. We're going to assume that air is the operating fluid. So let's draw a gas turbine engine here. And say I have a compressor. I have a turbine. Have some shaft, I have another shaft right here. I'm gonna get some work out, and I have some combustor here, but I'm not gonna treat it as reactions. I'm gonna treat it as heat exchanger for now. So we're gonna say, I'm gonna write it on the side here, heat exchanger. I'm gonna treat it as heat exchanger.
Professor?
Yes.
Can you put in a presentation of light?
Oh, okay, yeah. Thank you for that. Oh, much better. Thank you. Heat exchanger, which what the heat exchanger are gonna do is primarily we're gonna add heat, some Q in, and I have my input gas is gonna come right here, so this is gonna be my station 1. This is gonna be my station 2, right here. And I'm gonna go into my turbine right here, station 3. And I'm gonna exit station 4. Now we can exhaust it to ambient like we do with propulsion systems, but just for the sake of keeping things simplified, let's, in terms of heat exchangers, let's do a cooling heat exchanger here. So we'll say cooler, and we'll say Q out. Okay, now, does anybody know why we draw a compressor like that and a turbine like that?
One expands, one compresses.
Very good. So where did you see that before? Or where did you learn about this? Sorry?
Thermo.
Thermo. Okay, so did see this. So I am wasting my time. Okay. All right, so why is it drawn like this? So when you look at the actual compressor, this is actually the shaft that's inside right here. This is what the shaft is like, right? This core thing right here. And the blades are actually placed like this. So with this flow path, what are you getting? I mean, you're restricting your flow, so therefore your pressure is actually going up. And vice versa when you're going into the diffuser. It's like this, or the turbine. So this is your shaft, and these are the turbine blades. And I'll show you examples of it later on, but that's essentially why we draw it like that. Because we're considering that there is a shaft right here, and the blades are, the area is actually going smaller when you have blades that are rotating, forcing the flow in that direction. We'll get into the details of components later on, but that's why we draw it that way. Back to our assumption, so this is a propulsion system. We're going to assume ideal gas. We're going to assume constant specific heats. We're going to neglect kinetic energy and potential energy. We're going to assume steady state. And we're going to assume adiabatic compressor and turbine. I cannot assume adiabatic combustor and cooler because if I do, then, well, I don't have this issue. All right, so how do I go and solve this problem? So I'm going to keep this up, but at some point I want to keep this always up there. The first thing you want to do is draw your enthalpy entropy diagram. All right, so when we drew the entropy enthalpy diagram, what do we use for reference in pressure, right? But for an engine like this, what am I supposed to do? So we drew it for simplified components. But for this one, it's a closed loop cycle or open loop cycle? Those are open. Closed, right? I circulated the gas back in there by having a cooler to simplify things. Propulsion is a system, yes, this is open, but you could make assumption that, well, you're dumping it into the ambient, and the ambient is actually temperature is down.